When we picture space, we tend to imagine a perfectly empty vacuum. But if you look at this image of the Earth's horizon, you can see our atmosphere stretching far out into low Earth orbit. This environment creates a constant physical challenge for anything in orbit. A spacecraft traveling at 17,000 miles an hour is constantly colliding with these atmospheric particles, creating a drag that slowly but surely pulls them downward. Right now, high solar activity is heating and expanding this atmosphere. This is causing the 20-year-old Swift Observatory to fall back toward Earth much faster than anyone anticipated. Orbital decay isn't just a theoretical concept, it's a physical friction that is currently dragging a vital piece of astronomical infrastructure toward the atmosphere, where it will eventually burn up. The Swift Observatory has spent 2 decades hunting for the most elusive events in the universe, gamma-ray bursts. These are the most powerful explosions in the known cosmos. In just a few minutes, a single burst can emit as much energy as our sun will generate over its entire 10 billion-year life. Scientists believe these bursts mark the collapse of massive stars, the very moments where heavy elements like gold are fused and formed. Swift acts as space's first responder. It spots these flashes instantly, before the light fades away. Once it locks onto a burst, it beams the coordinates down to Earth, allowing other telescopes to swivel around and study the event before it disappears. If Swift is lost to the atmosphere, we lose our immediate warning system for the universe's most extreme events. For decades, mission control followed a standard rule. When a satellite's orbit finally decayed, you simply watched it burn up. Catalyst Space is testing a different strategy, treating orbital decay as a problem to be solved rather than an inevitable conclusion. They assembled their rescue spacecraft in just 8 months for about $30 million, a relatively small budget for a mission of this complexity. The rescue craft will launch and rendezvous with Swift in orbit, maneuvering to match its speed exactly. In position, it extends small robotic arms to grab onto the telescope. Then, its thrusters push Swift back to a higher, safer altitude. This has never been attempted before. Neither NASA nor Catalyst has ever used a robotic spacecraft to physically boost a satellite's orbit. It is a high-risk, low-cost experiment, and the results will determine if this method of orbital rescue is actually viable. If the mission goes as planned, Swift should be secure in its new orbit by September. But the implications go far beyond saving a single telescope. Swift is effectively a proof of concept for maintaining the entire orbital ecosystem. The most famous candidate for this technology is the Hubble Space Telescope. Like Swift, Hubble is fighting atmospheric drag. Current projections suggest it will re-enter the atmosphere sometime in the early 2030s. Rescuing Hubble would be a much larger task, requiring a bigger spacecraft and more thrust than the mission launching for Swift. However, if Catalyst proves that robotic arms and thrusters can save Swift today, they provide the technical foundation needed to save Hubble tomorrow. Mastering this process opens the door to a future where we can refuel, repair, and relocate aging satellites instead of just replacing them. Success with Swift provides a working blueprint for extending the life of our orbital tools. It suggests that with a relatively small investment, we can keep our existing infrastructure functioning long after its original expiration date.